All right, so welcome to this video on example number 4, where we're trying to integrate this function x squared over region E that is above x squared plus y squared plus z squared is equal to 36, and inside z is equal to negative square root of 3x squared plus 3y squared. All right, so first thing here, right, we don't really know anything except for we are looking at x squared plus y squared plus z squared is equal to 36. All right, so what does that represent here? Well, that represents a sphere, right? So this is a sphere of radius 6. So let's go ahead and sketch that one. So we have this sphere here, right? And if you go to CalcPlot 3D here and you go ahead and sketch that one, what you should be getting is you're going to be getting an upside down cone here, right? So what you're looking at, you're looking at the region inside, above the region x squared plus y squared plus z squared, but inside this cone here, which means the region you're getting really is an upside down ice cream cone with a little bit of ice cream there. All right, so again, this one here is a cone. All right, so if I rewrite this, I could pull out a negative square root of 3 from there. Then I'd be left with square root of x squared plus y squared. That might be a little more familiar. So I have z as a constant times square root of x squared plus y squared. So we would believe that that's a cone. All right, so what we're looking at, the region we're working with is this thing here. All right, so before we proceed here, we are integrating in a region involving a sphere. That means it makes sense to use spherical coordinates, right? So what we're going to do is we're going to use spherical coordinates. If we are going to use spherical coordinates, that would mean we would need to figure out the bounds in spherical coordinates, right? So if you look at this one here first, so for rho, we see automatically that the smallest it can be inside is 0, the largest it can be is 6, so rho is going to go all the way from 0 to 6. All right. So now, next up is there any restriction on theta? All right, so we don't quite know that, so what we're going to do is first we're going to look at phi instead, and we're going to analyze this equation here, or this one here. All right, so we have run into this quantity here, x squared plus y squared, quite a few times, right? So let's look at this one here. So let's try to understand what x squared plus y squared looks like in spherical coordinates. Remember, x squared is rho sine of phi cosine theta squared plus y is rho sine of phi sine theta squared. Right, so if I square both of them, I get rho squared sine squared of phi cosine squared theta plus rho squared sine squared of phi sine squared theta. Right, so is there anything we can factor out there? Yes, there is, right? So this is rho squared sine squared of phi. I'm left with cosine squared theta plus sine squared theta. And if I add cosine squared theta plus sine squared theta, I'm going to be left with rho squared sine squared of phi. So what we have is we have x squared plus y squared is equal to rho squared sine squared of phi. Right, so in particular then, square root of x squared plus y squared is positive rho squared sine squared of phi. And remember, rho is always positive, so it becomes rho. And Phi always has value between 0 and pi. Remember, that's the limit for phi. It's always between 0 and pi. And when phi is between 0 and pi, sine is always positive as well. So when I take it outside the square root, I get rho sine of phi. All right, so in general, when we're looking at spherical coordinates here, square root of x squared plus y squared is rho sine of phi. Right, so let's now go and look at this equation of the cone here. So we are looking at the cone. Z is equal to -3 square root of x squared plus y squared. All right, let's replace what we know. We know Z is equal to rho cosine of phi. And this is -3 x squared plus y squared is equal to rho sine of phi. Sorry, this should be it should be negative square root of 3. Sorry, negative square root of 3. Right, and what I'm going to do is I'm going to move everything over here, so I get 1 over negative radical 3 is equal to rho sine of phi over rho cosine of phi. Which means if the rho cancel out, sine over cosine is tangent, so I get tangent of phi is equal to 1 over square root of 3 with a negative. Right? And the angle for which tangent of phi is equal to -1 over radical 3 is going to be phi is equal to 5 pi over 6. All right, so this cone here that we're looking at in spherical coordinates is given by phi is equal to 5 pi over 6. This is given by rho here. All right, so we already knew the bounds for rho. Right, so next up what we would like to do is we'd like to find the bounds for phi and for theta. All right, so let's look at theta here first. Was there any restriction that we got on anything here in terms of x and y? All right, x squared plus y squared plus z squared is equal to 36, but x can be both positive and negative. There's no restriction on it here. So in this case, theta, there's no restriction, and in general, since theta can be between 0 and 2 pi, that's what we're going to get here too. All right, so that's for rho, for theta. Now let's look at for phi. Right, and that's this was always the difficult one here, right? All this work here. So we are looking at this upside down ice cream cone here. Remember, this is phi is equal to 5 pi over 6. If I want to be inside this cone here, should the angle my points make with the positive z-axis be bigger than 5 pi over 6 or less than 5 pi over 6? Right, so if this boundary here that I'm looking at makes angle 5 pi over 6 with the positive z-axis. If I want to be inside the cone here, the angle I should be making with the positive z-axis should be bigger than that, right? So that means my lower bound for phi is going to be 5 pi over 6 phi, and there's no restriction on the other side because we're going to go all the way to the negative z-axis. Everything in there is included, so we're going to get p. All right, so that's the 3 bounds here that we're working with. Rho is between 0 and 6. That's because we had a sphere of radius 6 and there was no other restriction on it, right? So theta is between 0 and 2 pi, and phi is between 5 pi over 6 and pi. All right, so now let's look at this one here. So then the integral over region E of x squared dv, remember, we need to first convert this x squared into rho, phi, and theta, and fortunately we know what the conversion is. It's rho sine phi cosine theta squared, and that's my x squared. Then I have my Jacobian, which is rho squared sine of phi, and then I have d rho, d phi, d theta. Rho is between 0 and 6, phi is between 5 pi over 6 and pi, and theta is between 0 and 2 pi. Right, so let's rewrite this here again. So when I look at it, I get 0 to 2 pi, give myself a little space here, 5 pi over 6 to pi, 0 to 6. Let's collect the row terms here. So I get rho squared from here times rho squared. So I get rho to the 4th. I have sine squared times sine, which I have sine cubed of phi. And then I have cosine squared of theta. Then I have d rho, d phi, d theta. All right. So let's look at something here. I have a product of functions, one only involving rho, one only involving phi, and one only involving theta. Right? So in that case here, I can split it up, and sorry, that's one. And then I look at the limits of integration. That's a number, that's a number, 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 number. There's no relation between, so all the integrals here only involve numbers and not functions here. So like I said, since we have a product of functions only involving rho, only involving phi, only involving theta, and we're integrating over numbers, I can view this as three separate integrals. So from 0 to 2 pi of cosine squared theta d theta, from 5 pi over 6 to pi sine cube of phi d phi, and from 0 to 6 rho to the 4th d rho. All right, so now what we're going to do is we're going to evaluate these individually. All right, so let's start with cosine squared of theta. So we're looking at 0 to 2 pi of cosine squared of theta d theta. All right, and this is where our reading questions are going to come into play. Cosine squared theta can be written as 1 plus cosine 2 theta divided by 2 d theta. So whenever you have even powers of sine and cosine, so you have a product and you have even powers of sine and cosine, so the power of cosine here is 2, and really there's a sine with power 0 showing up, but anyways, there's only even powers here, we're going to have to use the double angle formula. So in this case here, cosine squared theta is going to be 1 plus cosine 2 theta. I can rewrite this as 0 to 2 pi. I'm going to do 1/2 plus 1/2 cosine 2 theta d theta. All right, so let's go ahead and integrate this. So integral of 1/2 is going to be theta plus 1/2 stays as it is. The integral of cosine 2 theta is going to be 1/2 sine of 2 theta. All right, where theta goes from 0 to 2 pi. All right, so again, whenever we're integrating even powers of cosine, that's going to be, or sine, we're going to use the half angle or the double angle formula. Now when I plug in 2 pi, this should be 1/2 theta, right? So I get 1/2 times 2 pi plus sine of 2 times 2 pi is going to be 0, minus, when I plug in 0, both of these are going to be 0. So when I do this, I'm just left with pi here. So the integral from 0 to 2 pi of cosine squared theta is pi. All right, so that's one of them here. Next, we are going to look at sine cube phi. So we're integrating it from 5 pi over 6 to pi of sine cube phi d phi. All right. So note here that we have an odd power of sine. All right. So if we have an odd power of sine or cosine, what we're going to do is we're going to save one copy of that power there. So what I'm going to do is I'm going to write it as sine squared phi times sine of phi d phi. All right, so what I did is I wrote it as sine squared phi sine of phi. If I multiply these out, I'm going to get sine cubed. But why am I doing that? Next, what I'm going to do is I'm going to take my sine squared of phi and I'm going to write it in terms of cosine. Right, so when I do that, I get 5 pi over 6 to pi. And sine squared of phi, remember, is 1 minus cosine squared of phi sine of phi d phi. And the reason we do all of this is now, if I make the substitution, u is equal to cosine of phi. Then du becomes negative sine of phi d phi, which means if I put all of this together here, I'm going to go from 5 pi over 6 to pi. And remember, I need this negative here, so I'm going to put a negative here. 1 minus cosine squared of phi, remember u was cosine of phi, so this becomes 1 minus u squared, and negative sine of phi d phi becomes du. Right? I can multiply the negative on the inside since I don't like carrying that negative all the way around, so I have 5 pi over 6 to pi, then I get u cubed minus 1 du. Sorry, u squared minus 1 du. All right, so again, let me pause here before we proceed. Whenever we have an odd power of sine or cosine, right, as soon as we have one of them, what we're going to do is whichever one has the odd power, we're going to save one copy of it. So in this case here it was sine, so I'm going to save a copy of sine here. Then I'm gonna have an even power of sine here. And for even powers, there's a nice relation between sine and cosine. That is, sine squared of phi is 1 minus cosine squared of phi. All right, so now that we are at this point here, we're going to go ahead and integrate this. So I'm left with u cubed over 3 minus u as we go from 5 pi over 6 to pi. And remember, pi u was cosine, so I'm going to be left with cosine cube of phi over 3 minus cosine of phi. And this is from 5 pi over 6 to pi. Alright, so let's look at this here. So I have cosine cube of pi. Cosine of pi is negative 1, so I get negative 1 over 3 minus 1 minus cosine cube of 5 pi over 6. And cosine of 5 pi over 6 is going to be negative radical 3 over 2. So I'm going to get negative radical 3 over 2 cubed divided by 3 minus radical 3 divided by 2. All right, and if I simplify all of this here, and put it in your calculator or do it itself, you get 2 over 3 minus 3 radical 3 over 8. Alright, so again, this last part here is not as important. You can just put it in your calculator and get an answer. But really, the reason I'm going through this in detail is because we never had a chance when we were doing integration to talk about integrals of trigonometric functions, right? Because we had not talked about trigonometry then. However, when we go to spherical coordinates, since we are doing a lot of trigonometry, it is vitally important that we're comfortable doing integrals involving higher powers of sine and cosine. All right, so those are the two, and the last one is relatively straightforward. We're integrating from 0 to 6 of rho to the 4th d rho, and that becomes rho to the 5th over 5 from 0 to 6. Right, so this becomes 6 to the 5th over 5 So when I put all of my integrals together, we get that the integral, which we're trying to evaluate, of e of x squared dv was, the first one was pi, then we had 2 over 3 minus 3 radical 3 over 8 times 6 to the 5th over 5. All right, so that's how we would go about evaluating that integral there. So again, it's an involved process here, right? So these spherical coordinates are not easy to work with. They're quite challenging. Like even once you figure out everything, I think, again, figuring out the bounds are the challenging part. Even after you figure out the bounds, these integrals are still a very involved process. Right? So this wasn't quite the case when we were dealing with polar or cylindrical coordinates, right? Once you figured out the bounds, the integrations were generally relatively smooth sailing. I mean, they were challenging. I'm not saying they're all easy, but nothing compared to this one here. All right, so take a look and you'll get plenty of practice with integration here next class. And if you have any questions on evaluating integrals over spherical coordinates or any coordinate system for that matter, please do swing by office hours. All right, so this will be the last integration technique we're going to be learning this term here. We were planning on doing Monte Carlo methods for higher dimension, but since we don't have access to MATLAB, we're going to scrap that this term here. So next time we're going to be talking about limits.